According to Bohr's model, what is the energy of the photon released when an electron jumps from the third orbit to the second orbit of the hydrogen atom? A. 13.6 electron volts, B. 1.89 electron volts, C. 10.2 electron volts, or D. 2.27 electron volts. According to Bohr, an atom releases one photon of light when an electron goes from a high-energy orbit to a low-energy orbit. The energy of the photon produced is equal to the difference in the energies associated with the orbits. For the hydrogen atom, Bohr derived the energy of the electron in the nth orbit to be negative 13.6 electron volts divided by n squared. In this problem, we are given that the electron jumps from the third orbit to the second orbit. So we calculate E for the third orbit. Negative 13.6 electron volts divided by 3 squared equals negative 1.51 electron volts. And we calculate E for the second orbit. Negative 13.6 electron volts divided by 2 squared equals negative 3.40 electron volts. The energy difference, negative 1.51 electron volts minus negative 3.40 electron volts equals 1.89 electron volts. Therefore, the correct answer is B. Here's a diagram to help you visualize this calculation. The energy of the electron in the third orbit is negative 1.51 electron volts. When it jumps to the second orbit, it loses energy and ends up with negative 3.40 electron volts. The amount of energy lost, delta E, is negative 1.51 electron volts minus negative 3.40 electron volts, or 1.89 electron volts. 1.89 electron volts of energy is carried away by a photon. This explains the red light with a wavelength of 656 nanometers that is produced by a hydrogen lamp. The series of lines produced by hydrogen in the visible region is known as the Bohr series. Bohr explains these lines as due to transitions of electrons to the second orbit from higher orbits. The red line corresponds to the transition from the third orbit. The blue line corresponds to the transition from the fourth orbit.